So hi there, I'm Hao, and this is just another video of me solving randomly code problem. So let's begin here. Okay, so the problem we have today is word search. Given an n by n grid of characters or and a string word, return true if the word exists in the grid. So the word can be constructed from letters sequentially in adjacent cell, where adjacent cell are horizontal and vertical neighboring. And then the same letter cell may not be used more than once. Okay, so uh, let's say we can look at O combination, right? We can use backtracking to solve this problem, right? So for each letter, A, B, C, E, S, F, G, S, A, D, E, right? So like for each letter, we can look at like the four words like this, right? Um, and what is our depth? Our depth would be the length of the word, right? So and we need to look at we need to do the backtracking for every single letter, right? So the time complexity would be n times n, which is like the matrix size here, right? We need to do the backtracking for every single letter, right? So this is the letters, and then the backtracking would be like 4 to the word length, right? Right. So number of path. So we have like four neighbors, and then the word length would be our depth, right? So each level would be like a letter. We're comparing a letter each in each level. All right. So if you look at here, we can see that the only valid solution that we have is A and A, right? Because the word starting at A, the word is A, B, C, C, E, D, right? And we're looking at A. So we can look at like the four option for the letter A here, right? Right. And there's no neighbors for top and left for A. So we only have B and S, right? But we need to check like for all neighbors. Okay, so for the second A, we don't have left and bottom. We only have top and right. Top is S and right is C, right? And from there, right, we can see that the only valid path that we have is so now this is the level 0, right? Index 0, and now we're onto the next level. Like we're looking at the letter B here. So only one option here, right? In 1, 2, 3, 4, only the B is valid, right? So we can keep iterating down from B. Okay, and yeah, similarly, we can. So for B, we have two neighbors, right? So C and F, right? Only one is valid, right? And we're looking at this. Then C, we have two neighbors, right? Sorry, we have three neighbors for C. Oh, sorry, for B, we have three neighbors. So we have B, F, and A, B, and F, right? So let me slow down a little bit here. So for B, we have three neighbors, which is F, A, F, and C, right? So A, F, and C, right? But they're not allow the letters to be used. They're not allowed the letters to be used more than once, right? So because in this single path, right, the letter A is already used, so we cannot use it again. So we can just use a visited set for each of the path, right? But that would make our space complexity like very bad because we need a set, a visited set for each and every single path, right? And that is like not very good. So the other thing we can do is that if we look at the constraint right here, we know that the board only consists of like uppercase and lowercase English letters, right? So we can mark the visited set, the visited letter to null as we iterate through it, right? So let's say we can set this one to null, right? When we pick that in this path, right? So other than that, the piece only have two paths now. So similarly, you can just keep going, right? So C is valid, like and we have so B is null, right? We visited B is null now. So C have two neighbors, C and E, right? And C is valid, right? We set C to null. We just go on to the next level, right? Two neighbors, C and E, right? E is valid, right? Yeah, and then so on and so forth. So when do we return? What is our base case? Our base case would be when we reach the length of, so our base case is when the depth of our recursion match is equal to the length of the word, right? Which means like we have found the word and we can return, right? And if we don't found the word, right? Let's say the S is invalid and we return here, we're just like gonna be return false here, right? Okay, so let code this up. Okay, so we want to do the backtracking for every single letter, right? So let's create a constant here for rows and columns. Rows is border length, and then columns is for 0 at length. Okay, so this is rows. Plus plus. Okay, okay, plus plus. Okay, and we plan to do the backtrack right for each element. So if backtrack right, and we're gonna return true. Otherwise, we will return false right at the end. Okay, so what do we need to pass in here? We want to. So if you look at the picture, three things, right? The first thing we want to know is which letter we are currently looking at, and we always start out at index 0, right? Which is like the first letter, right? So we can call this like the word index, right? And the other thing that we need to know is what letter we are looking at in the matrix, right? So the row and the column, the current row and the current column, right? So current row and current column, right? So that we can compare the word in the input word, and then we can compare the letter in the input word and the letter in the board, right? Okay, so the input, the word index would always be 0, right? And then we're gonna do the backtracking for each letter, so that's just gonna be like I and J. Okay, so call backtrack equal to the word index, right? Row and then column. Okay, so what is our base case? Our base case is okay, so we need to make sure the row and the column inbounds, right? Because as we keep iterating, we will increment our row and column, and if they are not outbound, we will just gonna go ahead and return false. So if it is like not inbound, row and column, right, we will return false here, right? And we also want to return false when the word is different, right? The word index is different than the fourth at row column, right? And we need inbound function here. Inbound, right? Column, right? We can return row greater than or equal to 0. Therefore, columns and rows is to be less than rows, and columns need to be less than columns. Right. And this is inbound. Okay, so that is our base case. If the word are not the same, we sorry, if the letter is not the same, we just return. Or if it is outbound, we also return, right? You can look at the result here. Right, so there's four possible paths, right? So the first one is we look at the left neighbor, and then the right neighbor, the top and the top neighbor and the bottom neighbors. So the word index would be the next word, right? So if we don't return, which means we are inbound and the word at word index is equal to the letter at the word index um, is equal to the letter in the board, right? At the current row and column. So we just increment the word index by 1, and then we will look at the left neighbors or the right neighbor, and then uh, top neighbors, right? And then the bottom neighbors. So if we have the result, right, and then we can return true. Or then let's just don't code this result, code this if a word exists, or if word exists, we return true. Okay. And remember that I mentioned earlier that we are not allowed to use the same letter again, right? So we can have a new set for like every single path, but that would be too space consuming, right? So what we can do is that we can set the space. We can make a copy of the current letter. So let's say copy that letter, right? Equal to the board at the row and column, right? And we can set the board at row and column to null, right? So in this case, even if the the row the cell at that the letter at the row at this row and column is selected again, it will be null and will be invalid, right? It's not gonna equal to the letter in the word input, right? So we can set it to null for comparison, right? And then after that, after the backtracking, we can set it back, right? To the copy letter, right? Uh, does it make sense here? Let me double check. Okay, we set the cell to null, and then after the backtracking, we want to set it back to the letter. Okay. Yeah, we want to set it back to the letters, right? So um so yeah, let's say we do the A, B, C, D, E, D, right? So this is our word, right? So let's say our word is A, B, C, C, E, D, A, right? Which is like this path, right? So we look at the letter A, right? The first one is letter A here, right? Hello? Oh, yeah, sorry. Technical issues. Okay. So yeah, let's say we look at the letter A here, right? And then we keep backtracking, right? And then this path is invalid, but this path is valid, right? So when we remember when we iterate through when we backtracking, we go down the recursion tree. We want to set the node we visited to null, right? And after we realize that like this path is invalid, right? We want to return back, right? So when we return back, we want to set uh, this cell to the previous value, right? Which is A. Like if we don't set it back to the copy letter, this will be still null. So when we iterate through A B B C E D E, right? And then when we get to the last letter, which is letter A here, then this null will be invalid, right? We need to use this letter again if the path is invalid. So we need to set back the copy letters. Okay, so let's give it a try here. Okay, something is not right. All right, let me double check my logics here. Inbounds. Okay, that's correct. We iterate to the rows and the columns. And if backtrack, we return true, otherwise we return false. That's right. In the backtrack, we have the word index, the row and the column. If it is not inbound, we return false. Or if the letter at the word index is different than the letter at the bar at the current row and column, so we also return false for that case. We make a copy of the letters at that cell, at the current cell. We set the cell to null. We increase the index, the word index. We look at the left neighbor, the right neighbor, the top and the bottom. Okay, we set it back at the end. And if we have the result, we return true. Okay, so when do we return true here? We never return true, right? So we are missing our base case here. Maybe you already realized that. So we have our base case for invalid, but what is our base case for a valid word? Which means that our word index is equal to the word.length minus 1, right? Do you return true here? So if it is inbound, so if this line is not returned false, which means we are inbound and the letter is the same, right? In that case, if it is the last letter, then we will return true. Accepted, submit, and it worked. Thank you for watching.